We think about controllers in a couple of different ways. And I think a lot of you are already experiencing this, kind of the different ways in which we think about things when you ask about, show me the math, or do an example where we work this out. I don't want to think with my brain and just like imagine what this thing is. I'm an engineer, I like formulas, right? So if you give me the formula, I can work it out. Then I don't have to think, okay? However, that is a little bit different from some other questions that I have seen. So for instance, one of the questions that is kind of perennial in this section of the work is something about how do I think about this thing called offset? And the people who are confused about the offset that we observe with proportional control are usually coming from a place of like, this controller is clearly broken. It's not working. If an offset remains, then the controller isn't working, and that's confusing, right? And I think it's useful to think about this in 3 different levels. And I'm borrowing these levels from a philosopher called Daniel Dennet. It's not important to know his name. It's not for exam purposes. But Dennett distinguishes between 3 different, what he calls stances. I'm going to draw them kind of from the bottom up. So there's basically the physical stance, which is also called the mechanical stance. And this stance refers to the idea that I am observing something. Okay, I'm scratching my head because I'm looking at something and I'm trying to understand what this object is going to do. I'm trying to understand how it works, right? And so at the very low level, when it's a thing like a cube, right, and that thing is falling, I can apply physical laws. So I can apply Newtonian mechanics, and I can say, oh, okay, if you tell me the mass of that cube, and you tell me how high it is above the floor, and you tell me a couple of other mechanical details about the system, I can plug it into my formulas, and I can tell you things. I can tell you how long it will take to reach the floor. I can tell you like what speed it will be going when it gets there. I can tell you all kinds of stuff mechanically. Then there's another stance. So the physical stance is the stance of objects, right? It's the stance of physics and chemistry and all of the kind of, let's call it hard sciences. Then there's this thing called the design stance. And this is kind of how we understand things like clocks. In other words, if I show you a clock, your first question will not be for me to open up the clock so you can observe the gears. If I ask you to predict where the minute hand will be 10 minutes from now, right? You won't say, give me a second. I need to understand every single gear in this mechanical device. I need to understand how the pendulum works. I need to understand where the gears are. There's a lot of computation going on in a clock, so I need to do all of that physics. Almost nobody does that, right? They understand this is a clock. It is designed to tell the time. The minute hand is designed to sweep at 1 minute per minute on the dial. And so if it is working as designed, I can predict very confidently from the design stance by saying, well, it's a clock. I understand what it's supposed to do, right? And so because it's supposed to go 10 minutes, the minute hand is supposed to move 10 minutes on the hand in 10 minutes, that prediction is now easy, right? And so the design stance is how we understand complicated systems that have been designed for a purpose. We reason backwards from the purpose, and we assume that they are working as designed. And this is actually how you interact with most of the complicated systems in your environment these days. If you're talking about built systems, how do you know how your microwave works? How do you know how your TV works? How do you know how an app on your phone works? You reason backwards from what it's supposed to do. You're like, oh, okay, this is a thing that is supposed to allow me to crop images. So there must be a place where I should select where those images are, and there must be a way for me to select what the crop area is. And so like there should be some kind of a place where I select all of these things, and there should be buttons that allow me to do that. And so, you know, what does this button do? Well, it probably does, if it just says go, right, like, and the app is called Image Cropper Plus, then the go button probably crops. Right? It doesn't have to be spelled out that much because I'm reasoning through this whole complex chain of like, this is what it's supposed to do. And this is where people make a mistake when we think about controllers as being specifically designed for a purpose which is unachievable. In other words, if we think that the controller is supposed to work perfectly, we will make mistakes when we predict what it will do. Because as we discussed in a previous lecture, the perfect controller is mostly impossible to build. And so every controller will only control imperfectly. There is no controller that you can buy that will always have the reference and the controlled variable lying on top of one another. Right? They'll get close, but they won't be on top. And like actually a certain part of what we're thinking about in this subject is how do we make that as close as we can? And for different kinds of strategies, for different designs of controller, what kinds of ways, in what ways do they deviate from this ideal behavior? Okay? And in chapter 10, we're going to be making this leap. We're going to go from where we are now, where I think most of you are still kind of in the design stance. You're reading the material and you're like saying, oh, this is what it's supposed to do. You're reading a physical description, but you aren't really thinking about simulating that physical level. You're still kind of thinking, well, it's a controller. It's trying to do something. And I think there's another layer. The last layer is the intentional stance. And now I'm going to draw a terribly... Okay, that's supposed to be like a vicious lion or something, right? This is how we understand things like things that are trying to kill us, right? If I reason about something that I encounter in the wild, I don't reason on the design stance, I reason on the intentional stance. What this means is I say something, my argument goes something like, this is a lion, it wants to eat me. And if I were a lion and I wanted to eat me, I would run towards me rapidly and bite this thing, right? And then you kind of, so you ascribe intent to the other thing. You then reason about their behavior through the intent, through saying, well, they want to kill me or they want to eat me, so they'll run towards me. And then you're like, well, I don't want to be eaten, so I'm going to run away. And I'm going to like climb a tree or something like that. Now there you're not necessarily thinking about, design. Now the interesting thing is that we are the best intuitively at the upper levels of this diagram. And as humans, we make mistakes towards the upper side very frequently. So people, you'll hear this, like I hear this all the time. Oh, my computer doesn't want to do this. I'm trying to make it do this and it doesn't want to do this, right? Now what's that? That's like, and it's so easy to go like a system up, to say, well, it's like, it's just being difficult, you know, like it's fighting me on this, right? Like we think about, and in fact we explain things to people that way as well, even when we know things are inanimate. So we will, how many times has somebody told you something like, oh, this thing is like trying to get to a low energy state, right? That's intentional reasoning. It's like, well, if I were a little ball and trying to get low, I would roll downhill, right? It's intentional, it's not mechanical. You're not solving differential equations. You're kind of ascribing desires and intent to that object. And then you're kind of reasoning through that. Now, this is the mistake that people make because a controller is much more like a rock than a lion. Okay? And so specifically when you think about something like a proportional controller, when you catch your mind saying, But why isn't it going, like it can see where the set point is, right? Its job is to go to set point. Why wouldn't it do that? You're thinking on the wrong level, right? You're either ascribing intent, you're either thinking there's a little man in the controller, and or like a little miniature version of you in the controller, and they're trying to make this happen, right? Or you're thinking, well, it's a controller, like a good controller would do this, and then you're like, why isn't this one doing it? Okay, and the answer is all the way at the mechanical level. That's how we can understand why this is happening, because firstly we have to understand that controllers are mechanical things or like electronic things, but they are like programs, right? And something like a proportional controller is literally like these 2 lines of Python code. Okay, that is like the intelligence of a proportional controller. It's not trying to do anything, right? It's not striving towards the set point. It's not like getting up every morning ready to do a little bit better this time, right? It is an inanimate, like 2-line little piece of code. And so there, when you're on the mechanical level, you can ask yourself, when you ask a question like, why will this not achieve set point? You should actually start at a question before that question. Like, why would this work at all? In what way does this work? And the answer is, when we look at these simple algorithms, the simple algorithms all work better under certain conditions than having no control at all.